We are going to look now at the connections. So you see the connections in this case. Um, we'll use this couple of examples that we have in here to illustrate this. And on the left-hand side, we have a hydraulic example, which is just a pipe that comes to a T. And then we have the direction of the fluids, and then we're going to see what happens. On the right hand side, we have an electrical system where you see the direction of the current. So let me disappear from here. And now we'll say, okay, let's put the title in here. We're interested in finding the block diameter. So this is going to be a hydraulic system. And this is going to be an electrical system. Okay, so what we are observing here is that, let's say this is a pipe, and you have two flows going into this connection, one of them going out. So in here it's very obvious that you could say that what's happening here. The first conclusion that we can reach is that f sub 1 plus f sub 2 is gotta be equal to f sub 3, right? That's the first conclusion that we can reach. So why don't we write it in here? I would say what came in equal to what came out, right? You could say another way to express this is to say that the summation of the flows equals to 0. That's the same thing. But because of Pascal laws, you could say because of Pascal's principle, isn't it true that the pressure 1 would have to be equal to the pressure 2 equals to pressure 3? Therefore, conclusion of this, therefore, let's just use another color. So in here, therefore, the flows sum the pressure is the same. Okay, so if that's true, we can say that in here in the block diagram form, we're going to adopt a convention to for every flow and every effort. You know, this is the we say effort E is equal to the pressure, and flow variable F is equal to the flow here. Okay, so what I would like to do is this. I would like to say In the pipe at the top, we have two variables. In the pipe on the left, we also have two variables. And the pipe on the right-hand side, we also have two variables. Where this is this is piece of 3 over here, this is piece of 1 over here, and this is piece of 2 over here. This is F1, this is F sub 2, and this is F sub 3. But you see, how is it connected? It says that F1 plus F2 is equal to F sub 3. So it's very obvious that in here, and also it says that P1, P2, and P sub 3 are the same. So why don't we do this? You know, I just say if these are the same, like that, you know, I just connect it like that. If you go in here, this is going to have a summation point. And then you have in here, like this. So you see, this is our block diagram of this connection. You see all three P's are the same, one connection. All the F's will add. But how do they add in here? It says that F1 comes like this, F2 comes like that, and F3 leaves like this. See? This is the way we see it up here, see? F1, F2 equals F3. So this is our block diagram here. Yeah. And if you relate this to a bond graph model, you will have a zero junction in here where you have the same three components, but in the bond graph notation, each one of these lines is like two of these. So in here, you're gonna have P sub 3 and F sub 3 over here, P sub 1 and F sub 1, and P sub 2 and F sub 2. If you put these arrows here like this, indicating which way we add things up, then we're fine here. But in bond graph notation, we use the half arrow, so I'm just gonna correct this for a second here. This is the way we do it. In here you have P sub 2 is like that, this is like this, and this is like that. Yeah. But the flow is this is how the flows add up, and it follows this notation. But in this case, one of these has to determine the effort like this, see? But the others will not have efforts but like that. So only one can set the effort to the zero junction. And this is our bond graph model. This is the equivalent of this. Yeah. What I would like to do is to is to try to do the same thing with the other example so that you can actually see it really well. I think it would be a good idea if I draw a line between this so we don't confuse this. Okay, very good. Any questions about what I just did? We can turn our attention to the electrical system. And in this case, in this particular case, we have to say that the currents add up, but the voltage is the same, right? So here, I1 is equal to I2 plus I sub 3, right? So this is, you will say in, and this is what got out. It's totally power conserving, so nothing gets lost. And then you know that what this is saying is that the summation of the i's equal to 0. That's what another way of writing this, because you could write that I1 minus I sub 2 minus I sub 3 equals to 0. You can do that, see? And then in here, we also know that the voltage V1 is equal to the voltage V2 equal to the voltage 3, because the voltage is constant at the node, right? So if this is true, you see it becomes easier to write it down in this form, in the block diagram form, where we have the summation of the currents equals to 0, but the voltage is the same. But what I would do in this particular case, I would say, okay, look, this is I on one side, this is the I2 on this side, and then we have the, so this I'll put it I1, I2, and this I sub 3. And in here you would put B sub 1, B sub 2, and B sub 3. But you see, all these B's are the same, right? So it follows that we could just join them. I like perfection, so let's just do it right. So just draw it again. I had it like this, right? Oh. Sorry. I had it like this. And what I was saying is we could just say, let's just join all this because they are the same. And we'll join with this. Yeah? But you see, i's will have to add. So the i's will have a summation pointing here where you have it like this. Again, I don't like that one, so we'll just do a nice one, a perfect one. In fact, this time I'm not gonna play around. We'll just do this one. How is that? Perfecto. There you go. So in this one, where we add this thing, we know that I1 is the one that comes in like that, right? And then I2 comes this way, and then I3 like this. This is the block diagram of this junction. But you can also represent it in, so let's just write it down in here. This is our block diagram. And then we have in here the 0 here. Like that. There we go. In here the i's will add. So this is I sub, no, this is the voltage, this case V sub 3 and I sub 3. I will write it on the top, the efforts, and on the bottom, the flows, on the left, the efforts, and on the right, the flows, so that just to be organized. So in this case, what do we have up there? We have it like this, that I1 is I2 plus I sub 3. So I1 comes in like this, and then these two go out like that. When you do that, it means that I1 is equal to 2 plus I sub 3. But we also need that V1 equals V sub 2 equals V sub 3. So any of this could actually set the effort. And for example, if this is the one that set it, then so the ones would be like that. And this would be our bond graph model of the same thing. As you begin to see, the bond graph notation is very compact compared to the block diagram notation. But this is the equivalency for this kind of junction.